So we have an AC circuit with a 450 ohm resistor. This is R. A 1.7 Henry inductor, that's L. And a 10 microfarad capacitor, that's C. It's oscillating at 50 hertz. If the source voltage is 220 volts RMS, so this is the RMS source voltage, we have a bunch of questions to answer. So inductive reactance. Inductive reactance is X of L, and it's equal to omega L. Omega is 2 pi F. F is 50 hertz, so it's 100 pi radians per second. So 100 pi radians per second times the 1.7 henries is 534. The units of inductive reactance is ohms. We're okay so far. Capacitive reactance. X sub C. 1 over omega C. So 1 over the 100 pi times 10 microfarads. That one ends up being 318 ohms. Impedance, you can think of as the overall resistance of the circuit. That's Z. It's equal to the square root of R squared plus the quantity of XL minus XC squared. So using R, XL, and XC, we find that Z is 499 ohms. Those are important pieces of information in order to find out the RMS current. The overall current in the circuit, the RMS value, is equal to the RMS source voltage over Z, over the impedance. Not over R. R is not the only element in the circuit. So the RMS source voltage, which we know is 220 volts, Z, which we have calculated to be 499 ohms, IRMS is 0.44 amps. So maximum voltage drop across the resistor depends upon the maximum current and the resistance. We have the RMS current, but we know RMS is equal to Imax over the square root of 2. So Imax will be the square root of 2 times IRMS multiplied by the resistance. The maximum voltage drop across the resistor is 280 volts. RMS voltage drop across the capacitor. If we want the RMS value, we need to use the RMS current. So the voltage across the capacitor, the RMS value will be IRMS times X sub C. We know IRMS, we know X sub C. So we know the voltage, RMS voltage across the capacitor, 140 volts. Maximum voltage drop across the inductor. Again, we'll need the maximum current, which is the square root of 2 times the IRMS. X sub L. Maximum voltage drop across our inductor is 332 volts. Questions on any of those? Okay on those? Average power dissipated in the circuit. We have a number of equations for average power. There's IRMS squared times R. There is IRMS times the RMS voltage drop across the resistor, specifically. There is IRMS times the RMS source voltage times the cosine of phi. Any of them work? If we use the first one, we already know IRMS, we know R. The power in our circuit is 87 watts. doesn't matter which equation you use, as long as you're, of course, plugging in the correct values for any of them. The power factor is the cosine of phi. Cosine of phi, either we can go ahead and do the second question first. Tangent of phi is XL minus XC over R. We know XL, we know XC, we know R. Take the inverse tangent. We find that phi is 25.6 degrees. We take the cosine of it, we'll have the power factor. Cosine phi is also equal to R over Z, by the way. So we can find it that way.
Can you also do the second cosine, or second cosine, arc cosine of R over Z?
To get this?
Same angle, yeah.
Yes. The only problem is, if you do the inverse cosine, you're always going to get a positive angle. But the angle could be negative, so you'll want to double check it.
So for the phase angle, you always use tangent.
Well, this one will give you the right magnitude of the angle. But yes, I would double check it using tangent to make sure you're getting the correct sign as well. In this case, it is positive anyway, so it works, no problem. Oh, I forgot to write down. The question is, does the current or voltage lead in this circuit? Whether the current or voltage leads, it all boils down to which one of these is bigger, XL or XC. If you remember our phasor diagrams, when XL was bigger than XC, our resultant vector for voltage ended up in the first quadrant, positive phi. A positive phi means voltage leads the current. If XC was bigger than XL, we would have ended up with the resultant vector down in the fourth quadrant. That would be a negative phase angle. And current would lead the voltage. Very last question, resonant frequency of this circuit. Please keep in mind frequency is in hertz. You'd have to ask for angular frequency if it wanted it in radians per second. But we know a circuit in resonance, omega is equal to 1 over the square root of LC. We know L, we know C. Omega ends up being 243 radians per second. That equals 2 pi F. So F ends up being 39 hertz. So we'd have to decrease the frequency a little bit to make this a resonant circuit.
So, in a nutshell, this is what we've been learning for.
So, on the test, I'm not going to ask you 12 different questions. I may ask you for current, for example, and maybe one of the voltages, and maybe some power. But please keep in mind, to get the current, you needed to figure out XL, XC, and Z. Those were required. So even though I may not explicitly ask you for XL, XC, or Z, you may very well likely need to find them to answer the other questions.